Hello and very good morning to all. Welcome back to this course of microengineering. And today in our 14th lecture, we will proceed further and we will explore the impedance matching circuit by making use of reactive element. That is, today we are going to see in this particular lecture how to design impedance matching circuit using stub element. So we recall from the previous lecture that we have designed the impedance matching network using a quarter wave transformer. So that time we discussed that the quarter wave transformers are very much efficient in order to match the given value of real value load to the given transmission line characteristic impedance. Okay. So in our previous lecture or in tutorial, we solved one particular example, and there I demonstrated you how to make use of a quarter wave transformer. Okay, and we solved that particular example using manual Smith chart. Okay, and we also verified the solution which we calculated manually using a simulator, and we found that whatever manual answer we got, that was a correct. So we go ahead next step, and we will see the next type of a matching circuit, that is the impedance matching circuit design using piece of transmission line, which is popularly known as a stub element matching. Okay, so first of all, we will go through a brief presentation of what do we mean by stub element matching, which is sometimes also known as reactive element matching, or it is sometimes also known with the other name as distributed element matching. Okay, so let us see what is that stub element matching. Okay, so I will put this on presentation mode. Now, stub element matching. So first of all, let us discuss a brief theory, and then we will follow a detailed design procedure, and we will see what are the different types of stub configurations are available. So stub matching or reactive element matching, it is a technique of impedance matching in which a piece of a transmission line is used in order to design the matching circuit. So earlier we saw a piece of a transmission line we already used in quarter wave transformer, right? So this technique is similar to that, but using the stub element, we can match any given value of complex load impedance, right? So earlier to quarter wave transformer, we have gone through simple lumped element LC matching circuit. So there we utilized discrete values of inductors and capacitor. So lumped element matching circuit is especially useful whenever we are having the operating frequency up to 1 gigahertz. Okay. So lumped element matching circuit, they are preferred to design whenever we operate at lower frequency range in the microwave. Okay. So on the other hand, if we operate at high frequency, then lumped component becomes difficult to make use of, because exact value of inductor and capacitor we will not get. Okay. So in that particular case, the best option is to make use of a stub element. So the stub element or the piece of a transmission line is going to provide us certain value of a reactance or susceptance. Okay, so the desired value of susceptance or reactance is provided by transmission line. Okay, and by using this transmission line, we will construct a impedance matching network, which we call it as a stub matching, or it is also known as a reactive element matching. Okay, so the stub matching is also known as a reactive matching, or with some other name, as it is also known as a distributed matching circuit. The stub matching is very simple to design when it is compared to lumped element matching. You recall that in the case of lumped element matching, we need to know certain rules, and we need to follow the sign convention of susceptances and reactances based on where they are located. Okay, and we also need to remember 4 empirical equations in order to calculate the value of inductor and capacitor in either parallel or in series configuration. Okay, so there lots of memorization of the things are required whenever we design lumped element matching. So those memorization is not at all required when we go to design impedance matching network using a stub. Okay, so also there is another benefit of using stub matching, that the stub element does not require any specific frequency of operation, because whatever length and distances we are going to calculate in the stub element design, please remember that that can be expressed in a generalized way in terms of a wavelength. So we need not to specify any frequency over there, while this is not the case with the lumped element matching. In lumped element matching, if you recall, in order to calculate inductor and capacitor value, we need to specify exclusively the frequency. Okay. So in terms of this particular compulsion, the stub element matching is much more flexible, right? So the design of a stub element involves, so what is the design of impedance matching circuit using stub? So the design involves finding appropriate length of a stub position. Okay. So we need to find where we want to place a given stub. So that distance we need to find, we call this distance as location of the stub, and it is indicated by small d. Okay. And there afterwards, we need to find appropriate length of the stub so that it will remove the reactive effect in the circuit, and thus the circuit, it will give a purely resistive network. Okay. So thus the design of the stub is carried out in order to find its position and applicable length. Okay. So in all the different types of stub matching circuit, the aim or the objective of the design of the stub is to find the exact location of the stub where we are going to put that stub in the circuit. Okay. And there afterwards to calculate the appropriate length of the stub. So please remember, all the stub matching circuit, what is the design? The principle behind design is to find the location of the stub where we are going to place it, right? And then what is the length of that particular stub so that it will nullify the reactive effect. So all the design of the stub element is based on this particular principle. And this principle is applicable for all the types of stub element matching, no matter whether it is a single stub, double stub, or triple stub. So that we are going to see later on. Okay. So this is just the introduction about the stub matching or the reactive element matching. Now, in the next way, we want to classify what are the different types of stubs are available and what are their sub-classification. So in general, the classification of a stub matching circuit has three different parts, or there are three different configuration, you can say. We can make use of a single stub, or we can make use of a two stubs. We normally call it as a double stub. Okay. And we can make use of a three stub, which we call it as a triple stub. Okay. So please remember, each has one of the drawbacks. So that's why the other type of configurations are designed. So certainly there is a certain problem associated with a single stub matching circuit. So that we will see later on. So that's why we will be going for designing double stub. Again, in double stub, there could be some problems in the design. And that's why we will be going for another configuration, which is a triple stub. Okay. So as on when we come across those topics, we will discuss the advantages and limitation of those stub. Okay. So the single stub can be further divided into two types: series stub and parallel stub. Parallel stubs are also known with the other name as a shunt stub. Okay. Now similarly, the series stub can be designed by making use of short circuit configuration. And similarly, the shunt stub or the parallel single stub can be designed either in a short circuit configuration or open circuit configuration. Okay. In the double stub, normally series double stub is also possible, but normally parallel or shunt double stub is preferred over the series stub. And in that again, we can find two sub classification. The parallel double shunt stub can be designed with either short circuit configuration or open circuit configuration. And similarly, the triple stub, whenever it is required to design, it is always preferred to design in a parallel or shunt configuration compared to series configuration. Okay. And that can be also done with the help of either using short circuit configuration or open circuit configuration. Okay. So more about what do we mean by this short circuit or open circuit configuration of a stub, and what do we mean by series and parallel stub. So that will be getting clear to you in our subsequent slides. Okay. So for just time being, you remember that the stub are divided into three categories. You can make use of a single stub, you can make use of a double stub, or you can make use of a triple stub. Okay, so theoretically, almost all of the design solutions can be conveniently provided by double stub. So hardly there is a requirement to make use of a triple stub, because in all application 99% solution can be completely given by using double stub. Okay, so here we will see what do you mean by single stub, double stub, and triple stub, and what do you mean by series configuration and shunt or parallel configuration. And then we will see what is the concept of short circuit and open circuit. Okay, so we'll go to the next slide. Now, in this particular slide, all the configuration of single stubs are shown over here. Now here you observe three different diagrams. So these diagrams are depicting the circuit configuration for the stub. So first of all, on the left hand side, the first configuration is single short circuit series stub. So on my right hand side over here, we have a complex load impedance. Now a stub which we are going to place with this complex load impedance in order to match this complex load impedance with the characteristic impedance of a transmission line indicated with Z0. In the first figure, we have made use of this series stub. So here if you observe, what I did is I cut the transmission line, and in between a transmission line I inserted a piece of a transmission line. Okay, and this piece of a transmission line is short circuited at the end. So SC here stands for short circuit. Okay, so what I did is this original transmission line I cut, okay, into two positions, and I inserted a transmission line which is short circuited at the end. Okay, and this transmission line which I placed by cutting this transmission line is nothing but a stub element. Okay, so this particular element is a stub element. Now please remember, this stub element is located at a specific distance from the load, which is indicated by D. So small d here represents location of the stub from the load. Okay, and capital L over here, it indicates what is the length of that particular stub. Okay, and at the end here, this particular transmission line is short circuited and it is indicated with SC. Okay, so a series single stub is the stub which is placed in series with the load impedance. Please remember. So always a series stub is placed in series with a load impedance in order to provide impedance matching to that complex load impedance, so that it will get matched with the characteristic impedance on the left hand side. Okay, so the first diagram clearly indicate that a stub is placed in series with the load impedance. So that's why it is called as a series stub, and we have used such a single stub, so that's why it is called as a single series stub. And this stub is short circuited at the end, so that's why the name of the configuration is single series short circuit. Okay, so this is called single series short circuit stub. Next, in the second diagram, it is a little bit different. Now, what common thing we find that the load impedance is as it is, the characteristic impedance of the transmission line is also as it is. Okay, now here what I placed a parallel stub. So these two blue lines, it is indicating a piece of a transmission line which is placed at certain distance d from the load impedance. Okay, and how it is placed? This transmission line is placed in parallel with the load impedance. Please remember. So that's why this is called as a parallel stub, or it is also known as a shunt stub. And how this transmission line is kept? The transmission line is kept open circuited at it both ends. So that's why it is called as a single shunt open circuit configuration. So this is a single stub, this is a parallel stub, and this parallel stub is kept open circuited at the other two ends. Okay, so here also, in order to design the stub, the design of the stub involves, as we discussed already in the previous slide, we need to find this distance or the location of the stub, right? And we need to find the length of the stub. So here the distance and the length are common in order to calculate the design of a particular stub. Now coming to the third configuration over, it is similar to the second configuration except the change that this stub, which is indicated with two blue lines which are kept in parallel with ZL, they are short circuited at their other end. Okay, and SC stands for short circuit, OC stands for open circuit, right? So this third figure is same as that of the second figure, only the change is that the stub, which is parallel, is short circuited at the end, and this will give us a single shunt short circuit configuration. Okay, so I hope that you have understood how to draw the stub configuration in a circuit configuration. Okay, so the first is a very common, that is a series stub. Please remember, series open circuit stub we are not going to make use of because it doesn't make any sense to keep the series stub in an open circuit configuration. Okay, so the first is series short circuit configuration, single stub. Second is a single shunt open circuit stub. Third is a single shunt short circuit stub. So what I request you people to take quickly these diagrams to be drawn in your notebook. So I request you people to quickly jot down these diagrams in your notebook so that later on, whenever we design a particular example and when we draw a schematic, you should remember how this circuit look like. So these are the all possible single stub configuration. Please remember, we are not using single series open circuit configuration because it doesn't make any sense. Okay, so we will prefer to make use of single series short circuit stub design, and the remaining two are parallel open circuit and parallel short circuit single stub both. Okay, so quickly you take down these diagrams because later on as on when we solve the example we need to draw the figure, and these figures are being used in order to represent the circuit diagram of single stub matching circuit. Okay, so I hope that you have taken down these configuration. I will move ahead. Next, coming to the double stub configuration. Now, as I already discussed, double stub can be also designed in a series configuration, but we don't prefer to make use of a series configuration. So why it is so? So we will discuss it later on, because in order to design a series stub, please remember, we need to cut the transmission line and there we need to insert the piece of stub. So this is a very difficult task in comparison to the parallel stub, where whenever we want to design a parallel stub, we need to just solder a piece of a transmission line at an appropriate place. So this process is much more easy when it is compared to the design of series stub. So that's why this is the main reason why we should prefer to make use of the parallel stubs in comparison to the series stub. So here the double stub configurations are shown. First double stub configuration is a double stub parallel or shunt open circuit, and the second configuration is double stub shunt short circuit. Okay, so what is the difference over here? See here again we have the same load impedance. Okay, and the first line indicate whose length is given by L1. Okay, so this indicates the length of the first stub. Now please remember, this first stub, which is indicated with a length L1, may be located on the load impedance itself. In that particular case, capital L is going to be 0. Okay, and there could be another possibility that the first stub, whose length is indicated by L1, is located at some distance away from the load, where in that particular case L is non-zero, capital L will become non-zero. Okay, so these two cases could happen with a double stub. Okay, and the separation between the first stub and second stub is indicated with small letter d. Okay, and these two stubs are kept in parallel with the load, so that's why it is called as a shunt stub. And these two stubs are kept open circuited at their other ends, so that's why this configuration is an open circuit, right? So L1, capital L1 is the length of first stub, capital L2 is the length of second stub. The stub number 1 and stub number 2, they are separated with a distance d. Okay, sometimes the stub number 1 is located on the load itself. In that particular case, capital L is going to be 0. In other case, if the first stub is located at some distance away from the load, in that case the L becomes non-zero. Okay. And what we observe the difference in the second configuration, the difference is only that these two stubs are short circuited at their other ends. So the short circuit is represented by letter SC. Rest of the configuration is as same as that of the open circuit configuration. Only the change in the second configuration is at the end of two transmission line, that is a piece of a stub, we have performed the short circuit, right? Now please remember again we will discuss whether open circuit configuration is preferred or short circuit configuration is preferred. The reason and the answer is short circuit configurations are always preferred, because short circuiting the line at the end will remove the effect of picking up the stray capacitance which will get formed in between the two pieces of a transmission line. So normally the short circuit configuration is preferred over open circuit configuration because of this reason, right? Now we go ahead and let us see how the triple stub configuration look like. So the triple stub configuration is in front of you. I will put the presentation mode. Okay. So the triple stub configuration look like similar to double stub configuration. Only the thing is that we have added one more stub into the configuration. Okay. So triple stub shunt open circuit configuration is shown on the left hand side, and triple stub shunt short circuit configuration is shown on our right hand side. Now please remember that similar to double stub configuration, here also we can make use of series stub. But as I already told you, series stubs are not preferred when it is compared with a shunt stub. So here we will show the configuration of triple stub in terms of shunt configuration only. And this shunt configuration can be kept open at the other end, so which will give us the first configuration of open circuit, or it can be short circuited at the other end in order to give us the short circuit configuration, right? So as on when we come across the double stub configuration, so the double stub configurations are preferred because the single stub in certain cases is not going to provide us a solution. So in that particular case, we will see why the single stub is not going to provide us the solution. So in that particular case, normally 99% of the solution for the impedance matching will be provided by the double stub. Okay. So when we come across the double stub design, we will clarify you why one should go for design of a double stub and why not for the single stub. Okay. And similarly, double stub also suffers from certain drawbacks. So that's why triple stub comes into the picture. So when we come across the theory of a triple stub, please remember we are not going to solve any particular example of designing a triple stub. It is just the addition of a single stub into the configuration of double stub. So we will see what is the drawback of a double stub, and we will discuss a theory. In order to come over to that particular drawback, we will design a triple stub theoretically. Okay, so though we are not going to solve any particular example on triple stub, okay, but definitely we will solve a couple of example manually on designing of double stub tuning circuit. Okay, so please remember stub matching circuit are also known as a tuning circuit or reactive element matching circuit. So all these terms, they are describing the same phenomena. Okay, so we move ahead and let us see what are the general rules for designing a stub matching circuits. So in this particular slide, we will discuss the generalized rule that one can follow for designing of a stub matching circuit or stub tuning circuit, right? So what is the design rule? First of all, for design of a series stub, please remember all these rules are very important. So first rule is that, and please remember these all rules are applicable for all types of stub matching, no matter what type of stub configuration it is, right? So when we design a series stub, please remember that time we will deal with the impedances. When we design a parallel stub or a shunt stub, then we will deal with the admittances. Please remember, we are not going to play with the impedance But whenever we are asked to design a parallel or shunt stub, we will deal with admittance. Okay, so therefore the plotted impedance need to be transformed to the admittance. So there we need to perform a conversion. Okay, because we have been supplied with the impedance and we are asked to design a parallel stub. In that particular case, we need to convert the given impedance into admittance. So this process we normally call it as a impedance transformation process, right? So the third rule, we can either make use of an impedance Smith chart or we can make use of combined Smith chart also. Okay, so there is no hard and fast rule that one should go utilizing a particular type of a Smith chart, whether it's Z chart or ZY chart. You can make use of any chart in order to design any type of a stub element. Okay, so if you remember, at the time of designing of lumped element, we insisted that you should make use of combine or ZY Smith chart because the sets of resistance circles and conductance circles are readily available. And later on we shown you that how to make use of Z chart in order to solve the example of lumped element matching also. Okay, so there is no hard and fast rule that you should make use of a particular Smith chart only for a particular example. So the same is applicable in the stub matching also. So in order to design the matching circuit using stub, you can make use of either impedance chart or combine ZY chart. Okay, all the stuff involve finding their locations and exact length for the design of impedance matching. So as I already discussed, the exact meaning of stub design is that we need to find exact location of that stub and then we need to find the length of that particular stub, right? So here again I am explaining the reason why shunt or parallel stubs are preferred over series stub, because as they provide the advantage of easy relocation. Okay, so as I already discussed, series stubs are not preferred because in order to design a series stub we need to cut the transmission line and insert a series stub into it. Okay, so this process is difficult in comparison to the design of parallel stub, in which we need to just solder out a stub in parallel with a given transmission line, which is very easy work as compared to cutting of the transmission line. Okay, so the next thing, why short circuit configurations are preferred. The short circuit configurations of the stubs are preferred over open circuit configuration, as these short circuit configuration are going to eliminate the effect of stray capacitance which may be produced between the open circuit situation. Okay, so it is not a hard and fast rule again, but normally whenever it is asked to design a stub, we make use of parallel stub and parallel also along with short circuit configuration because it is going to provide us these two advantages. So these are the general rules for stub element matching or stub tuning, and this is applicable for all the types of stub configuration. We go ahead, and now this is the detailed design step for designing single stub matching. Okay, so in single stub matching, please remember we can design series stub as well as we can design shunt stub or parallel stub, and these design stubs are applicable for both types. Okay, so when we come across solving a typical example for series stub and parallel stub, you will come to know how these exactly steps are being followed, right? So for meanwhile, what I will do is first I will read out this design step for you. Okay. So if you are noting down all these steps, it will be better for you. Anyway, this video lecture will be available to you. You can refer to any time and you can jot down quickly these detailed design step for designing single stub matching circuit. So first step is we have been supplied with the impedance, right? So that impedance we will plot into the given Smith chart. Again, the type of a Smith chart doesn't matter. So how we input the impedance point into the Smith chart? By normalizing it. Okay, so the common procedure. Then we will read the problem statement. First of all, what type of design of the stub is asked. Okay, so whether a series stub is asked or whether a shunt stub is asked. Okay, so if we have been asked with a series stub, then we directly plot the impedance. Okay, on the other hand, if we have been asked to design a shunt or parallel stub, then the plotted impedance we need to convert into admittance, because already in the general rules we saw that whenever we want to design series stub, we deal with impedance, right? And whenever we want to design parallel stub, we need to play with the admittances. So how to convert the impedance into admittance? That can be done in step number 3 by drawing a VSWR circle. Okay, so we will see this procedure. Whenever we want to design a parallel stub, we need to first convert the plotted impedance into admittance, and this procedure we used to call it as impedance transformation. Okay, so once you transform the impedance into corresponding admittance, the Smith chart is treated as an admittance chart. But please remember, we will still follow the sign convention of the original Z chart for the imaginary parts. So please remember, this is a very important thing to remember. Then next is, what we need to find is, we need to find the wavelength towards generator value of the plotted impedance point in the case of a series stub, or admittance point in the case of a parallel stub. Okay, so we need to note down what is the wavelength toward generator scale, because we need to find the location of the stub. Next, what we do is, in order to find the location of either series stub or parallel stub, we will start moving on the VSWR circle always in a clockwise direction, so that we will get intersection with either unit resistance circle in the case when we are designing series stub, or it will be with unit conductance circle whenever we are designing a parallel stub. In both of these situations, when we get the intersection point with unit resistance circle or unit conductance circle, the real value we will get 1 with certain imaginary value, right? So we will note down what is the value of WTG at this intersection point, right? And then we will calculate the difference between the wavelength toward generator value at the given load impedance or load admittance with respect to this intersection point on either resistance circle or conductance circle of unit value. Then this difference of wavelength toward generator will give us the exact location of the stub. Okay, so the half of the solution is completed over here. Okay, so whatever I am explaining, so that thing will become clear to you when we solve a typical example. Okay, so the next job is now to find out the appropriate length of the stub. Now anyway we found out where is the location of stub. Now next is to find out the length of the stub. We need to note down what is the imaginary part value at this intersection point. Now what we want is this imaginary part value which we have got at the intersection point, that we want to remove. We want to make the intersection point value purely equal to 1. So in order to make it purely 1, we need to remove the imaginary part. So in order to remove the imaginary part, we need to add the same imaginary part with opposite polarity, right? So in the step 7, what we do is we will locate the reactance in the case of impedance, or we will locate the susceptance in the case of admittance of opposite value on the Smith chart. And at that particular point, again, we will read out wavelength towards generator, WTG scale. Okay. And then depending upon what type of configuration it is asked, whether it is short circuit or open circuit, then we will calculate the location of this particular point with the given open circuit or short circuit configuration, right? So we will follow a correct convention for Z and Y in order to locate either short circuit or open circuit condition. So in the next slide, we will see how to follow the sign convention for short circuit and open circuit situation for both, that is for impedance and for admittance. Okay, so that we will see in the next slide. Okay, and after calculating the length of the stub, then we should draw a schematic the way in which I have shown you in earlier slide, the diagram, schematic diagrams of the stub matching circuit. Then one of that circuit diagram, whatever it is asked in the whatever configuration, whether it is series or parallel, open circuited or short circuited, appropriate diagram need to be drawn with the neat labels, and that will finish the complete design of the single stub matching or single stub tuning. Now coming to the convention of open circuit and short circuit point. Please remember here, again I will repeat, whenever it is asked to design a series stub, we deal with impedance. And whenever it is asked us to design parallel stub or shunt stub, we deal with admittance. Okay. So here open circuit and short circuit configuration need to be followed with a typical procedure. So where is the short circuit point and open circuit point located for impedance as well as admittance? Let us see in our next slide. Okay. So here in this particular slide, we have the short circuit and open circuit point locations for impedance as well as admittance. If you recall, this particular Smith chart is a combined Smith chart, right? So here I have shown you the location of short circuit point and open circuit point for impedance as well as for admittance. Now we already know that the center of the Smith chart is always representing the matched point. Okay, so that is always representing the characteristic impedance of the transmission line with which we want to match the given load impedance, right? So on the right hand side extreme on the real axis, see on the right hand side extreme of the real axis, the value of impedance is infinite. So here at this particular point Z is equal to infinity. That indicates that impedance is infinite. So the infinite impedance, it acts as an open circuit. So whenever we want to design open circuit impedance matching circuit, then we need to take this point into account. Okay. As the impedance is infinity over here, what is the value of admittance? So we know that the admittance is a reciprocal of a impedance. So when Z becomes infinity, Y becomes 0. So the same point on the extreme right hand side on my real axis is representing Y is equal to 0 for short circuit condition. So whenever admittances are 0, it indicates short circuit. Okay. So here this location of the point is indicating two parameters at a time. So this point is representing Z is equal to infinity, as well as the same point is representing Y is equal to 0. Okay. And here wavelength towards generator value is always 0.25 lambda. Okay. So if you look at a particular Smith chart physically, you will find that WTG value on this extreme right hand side point is always 0.25 lambda. Okay. And the same is true for wavelength towards load at this particular point, right? So on the left hand side, on the extremity of my real axis on the Smith chart, I will find another point. Now this point is where the impedance is very low. It is as good as Z is equal to 0. Okay. So Z is equal to 0, or the point is representing short circuit condition for impedance. Okay. If Z is equal to 0, then we know that Y is equal to 1 upon Z, reciprocal of it. Then the admittance at the same point is represented as an open circuit or infinity. Okay. So this point is representing Y is equal to infinity. It is representing open circuit for admittance, and the same point is representing short circuit for impedance, right? So here there are two ways in order to take into account the wavelength toward generator scale. So there are two mechanisms with which we can read out the wavelength toward generator value at this particular point. Now please remember a very important thing. Whenever we start from this particular point going clockwise, okay, say please remember what I'm saying. So whenever you start from this particular point going clockwise, we need to treat the WTG value is equal to 0 lambda. Okay, so this is when we start from this particular point going clockwise. Okay, on the other hand, if we are approaching to this particular point from the downside like this, at that time we need to consider wavelength towards generator value of the same point to be 0.5 lambda and not 0 lambda. Okay, so these are the typical sign convention that we need to follow in order to locate the appropriate short circuit point and open circuit point for either given value of impedance or admittance, right? So the thing will become crystal clear to you when we solve a typical example. At that time, in the last procedure of the design of the stub, whenever we want to find out whether the stub is open circuited or short circuited, at that time we need to make this particular decision which point to be considered for placing either open circuit or short circuit with the given type of a stub. Okay, so I hope you understood all the basic theoretical formulation in order to understand and in order to design a single stub matching circuit. Okay, all these preliminaries and foundations are same required for the design of double stub, but they're a little bit lengthy procedure and a different procedure that we are going to follow. But all the principles and fundamentals of sign convention, considering the short circuit and open circuit configuration, the general rules of the stub matching are going to remain same to all the types of stub. Okay, so I hope with this you have understood all the basic foundation information which we need in order to design single stub matching element. And the same principles are again used whenever we go for design of higher configuration, that is a second double stub and triple stub configuration. Okay, so let us go ahead and see what is the next. Okay, so what we do is now we will solve a typical example. Now the first example, that is example number 5 in the sequence, the design of single series short circuit stub. Now you need to read it carefully. So we want to design a single series short circuit stub. Okay, so that means we need to play with the impedance because we want to design a series stub, right? This series stub is short circuited at the end. Okay, and we need to design such a single stub. So here the problem statement is given. So I request that you people have taken out enough number of hard copies of the Smith chart, and the Smith charts are right now available with you. Okay, so if it is not available, quickly arrange a blank and brand new Smith chart. You can either use ZY chart or Z chart, any of the Smith chart we can make use of. And here we are going to solve our first example of impedance matching circuit using first configuration, that is a series stub. That is also in a short circuit configuration. So a problem statement is in front of you. The problem statement I will first read out. The problem is a complex load impedance is given. The load impedance ZL is equal to 75 minus J80 ohm. Now this complex load impedance is need to be matched to the transmission line of having the characteristic impedance is equal to 50 ohm. Then it is asked us to design single short circuit series stub impedance matching circuit. Okay, so the problem statement, I hope it is very straightforward. We are asked to design single series short circuit stub in order to match the load impedance 75 minus J80 ohm to the transmission line of a characteristic impedance 50 ohm. So this particular configuration look like, come back to our circuit configuration. So here this first configuration that we are going to design. So the load impedance is given, ZL is given, okay, and the characteristic impedance of the transmission line is given, and we are asked to design this particular stub. Now designing of this particular stub is nothing but finding out the distance or the location of the stub from the load and finding the length of the stub. Okay, so as on when we finish a problem to calculate the location of the stub small d and the length of the stub L, Then we will complete the design example and we will redraw this same diagram with neat labels of the values of distance and length. Okay, so let us go ahead solving this particular example. I hope you people are fully equipped with your brand new Smith chart and the drawing instrument, including your compass, ruler, pencil, colored pen or sketch pen if you want to use it. So okay, so first of all, the thing is we need to write what are the given things. So the given things are what type of stub. We want to design series single short circuit stub. That means we need to deal with impedances. Please remember. The load impedance is given 75 minus J80 ohm and the characteristic impedance of the transmission line is given. Okay. So here we will make use of simple Z chart or impedance chart for designing of this example. So I hope that you also are going to make use of an impedance chart. I hope you are there with your impedance chart and all the necessary required equipments with you. Okay, so we'll be starting manually solving a design solution to this particular problem. Okay, so what I will do is I will open a brand new Smith chart. Yeah, I'm using the impedance Smith chart. I will maximize zoom into this particular Smith chart. So here, if you observe, I am making use of this impedance Smith chart, right? So this is a plain impedance Smith chart. Okay. So step by step, we will follow the on-screen instruction which is given in a PPT, and you will come to know what is the exact procedure of designing the impedance matching circuit, right? So here, next step, I will put in the presentation mode. Yes, so we need to follow these 10 steps. Okay, so these 10 steps, though it is visualizing exhaustive number of steps, so these are very easy to follow. Okay, so I hope that you are there with your Smith chart and all necessary equipments available. So I'll be solving this particular example manually. I hope you will follow me with a step-by-step procedure, and then we will find out our solution together. Okay. So the first step in the solution is normalize and plot the given load impedance. Okay. So after normalization, we will find ZL is equal to ZL bar that we are going to represent in the Smith chart. So the given load impedance we divide by 50 so that we will get some real part and some imaginary part, the way in which we did earlier. Okay. So what we do is after normalizing the given load impedance, we plot that impedance. So the impedance is 1.5 real part, which is represented by constant resistance circle, and imaginary part is a negative 1.6. So it will come in the downside of the Smith chart in the lower half. So 1.5 and minus 1.6. So take out your Smith chart. I will zoom in this Smith chart. So what is the real value? Real value of the chart is 1.5 and imaginary part is minus 1.6. So 1.5 circle over here you can visualize. So if you zoom in a little bit more into your Smith chart, so the resistance circle values are given on the real axis. So this is 1.4, right? This is 1.6. The heavy lines are indicating. So in between that, you will find a faint line representing some circle. So this line is nothing but 1.5. So the impedance that we are looking for is 1.5 and negative reactance 1.6. So where is the negative reactance here? So if you scroll down and come to the downside, so here 1.6 value is represented over here. You can zoom in and here you can represent that the reactance is negative. It will be indicated by this curve or arc. Okay, so we need to find intersection of 1.5 circle with this particular arc. Okay, so I will zoom out. Okay, so 1.5, So I will directly plot that particular point by tracing 1.5. So that means this circle, inside circle, and 1.6. Okay, so and 1.6. So where is a 1.6 is this line, right? And this is 1.5. So somewhere here is the point located. Okay, somewhere. See here, it is a 1.6, right? And 1.6, this line, and 1.5. Okay, so at the junction of 1.6 negative and 1.5, somewhere here, right? So I will take a pencil. You also do the same procedure with me. I will increase the brightness of the screen. Say, whenever we are solving the example manually and whenever you are observing the video, I request you people to put the brightness level of your screen to maximum so that you can visualize it clearly. So 1.5, this circle, right? And 1.6, so somewhere here, right? So here I will put that dot. Okay, so what is this point? This point is now representing ZL bar. This point is now representing ZL bar value. So I will write here as ZL bar, which is representing normalized load impedance value. Okay, so we have completed this step. We have plotted the complex load impedance. Second step is we need to design a series step. Hence, we use the impedance chart. So originally, what is this chart? This chart is itself a impedance chart. So we will be making use of the impedances only. Coming to the third step. In the third step, note down the value of wavelength towards generator at this particular plotted point. So how to measure the wavelength towards generator value at this particular point? So it is very simple. So come back to your Smith chart where you have plotted the ZL bar point. Okay. Now what you do is take your scale. Okay. Join the center of the Smith chart. Okay. Join the center of the Smith chart with this plotted value of load impedance. What you do is take your scale, join the center of the Smith chart with this load impedance and extend the straight line straight away on the periphery, external periphery of the Smith chart till it intersect across the Smith chart over here. Okay, so I will choose a different color. I will choose the yellow color. Okay, so I will join the center of the Smith chart with the plotted impedance and I will extend this straight line so that it will cross the periphery. Okay, I will remove the scale now. Okay, so now what you need to do is you need to read the value where this straight line, yellow straight line is intersecting to the outermost scale. Now please remember from the earlier discussion of Smith chart basic, the outermost scale represents wavelength towards generator when it is measured always clockwise. Okay, so here I will zoom in into this particular region. Now here you observe that the outermost scale of the Smith chart is representing wavelength towards generator value. So we need to read the value where this yellow straight line is going to intersect. Okay, it is clearly visible that the wavelength towards generator value is in between 0.3 lambda to 0.31 lambda. Okay, so each division corresponds to 0.002. Okay, so it is how many division after 0.3 the yellow line is crossing? 1, 2 and approximately 3. Okay, so this will be 0.302, 304 and 0.306. Okay, so what value we will get? The wavelength towards generator, we get WTG to be 0.306 lambda. So the same I will write over here. So I will use a different color. So WTG over here, I will write here as WTG. What WTG stands for? WTG stands for the measured value of wavelength towards generator, wherever this yellow line is crossing on the outermost scale. Okay, and the value is 0.306. 0.306 lambda. Please remember, always try to write in terms of wavelength, lambda. Okay, so this we completed. So why we are doing so? Because we want to find the location of the stub from the load. So that's why we are performing this particular procedure. Okay, so come back to the next step. We have noted down step number 3 and we have got the same value of wavelength towards generator. The next step is to draw a constant VSWR circle which is passing through normalized load impedance. Okay, so what is the next procedure? Next procedure, come back to your Smith chart. I will adjust the Smith chart now. Okay, so the next procedure is we want to draw a constant VSWR circle which will pass through ZL bar. Okay, so what you do is now adjust your Smith chart. I will draw a constant VSWR circle which is passing through ZL bar. You know the already procedure. You take your compass now, put metallic part of your compass at the center of the Smith chart. Put metallic part of the compass at the center of your Smith chart in this way, right? Take distance in your compass from the center of Smith chart to ZL bar point. I repeat, take distance in your compass from the center of Smith chart to ZL bar point. Okay, so in this way, right? So once you have taken the distance in your compass from the center of Smith chart to the ZL bar point, then you draw a constant radius VSWR circle. Now for drawing VSWR circle, I prefer to make use of this lime green color. If you have colored pen or colored pencil or sketch pen, try to make use of the same. Okay, so you can use any color whatever you like. So for understanding purpose, I will be making use of a different color configuration and convention. Okay, so I will draw a constant VSWR circle, right, in this way. So whatever green circle that you are observing in the Smith chart now, it is representing what? It is representing the VSWR circle. Please remember. I will draw from here, this side, in this way, approximately you can draw, right? Okay. And then you can remove the compass. Okay, so whatever green circle here we observe, this green circle is nothing but a constant VSWR circle, which I have just right now drawn. Okay, so we have completed the step number 4. Okay, so we have drawn a constant VSWR circle. Okay, now the next step is now start tracing on this VSWR circle from ZL bar in a clockwise direction until we intersect unit resistance circle at point number 1. Okay, so what we do next is we'll open the Smith chart. I will zoom in into this particular area now. So what I will do is put a cursor on this ZL bar and I will start traveling on this green VSWR circle in a clockwise direction. Please remember, always we need to move in a clockwise direction. So what you do is you have drawn the VSWR circle, right? Put your pencil on ZL bar and start tracing on this green VSWR circle clockwise. You need to trace till what point? Till you get the intersection with this unit resistance circle. Now you know unit resistance circle where it is located. So the unit resistance circle is this particular circle. Okay. So when I start tracing VSWR circle clockwise from ZL bar in this way, I will cut the unit resistance circle somewhere. Okay. So that point, denote it with point number 1. So I will choose black color over here. Okay, so here I will start tracing out in this way, and here we know this is a unit resistance circle. So here I will intersect. Okay, So here I will intersect. So call this point as point number 1. Call this point as point number 1. Okay, so that is what we are expecting. So here we call this point as a 1. Okay, and here what is the real value? Real value, it is located on a unit resistance circle, so real value is 1. Okay, so what is the imaginary value over here? So the imaginary value over here is close to 1.4. Okay, so here what is the value of real part at point number 1 is 1. Okay, and what is the imaginary value at point number 1? The imaginary value is closer to 1.4. You can take it approximately, it is not exactly 1.4, but this is closer to 1.4. Okay, and what 1.4 is representing? It is representing reactance, that is X, and the reactance in the below half of the Smith charts are negative. So here around minus 1 point. So here if you want, I can draw it with some blue color, and I will reduce the thickness, say here approximately. So in this way, if you can go over here, you can go in a parallel with this line, and approximately it will come closer to 1.4. So actually it is a 1.39. So here you can write this value as around 1.39. Okay, so what this value is representing? This value is representing reactance at this point number 1, right? And this reactance, as it is located in the below half, it is treated as minus 1.39. So this reactance value X is written over here. So what we get the value? This value we have got minus 1.39. Okay, now please remember that there is a one more intersection point. Okay, say as we said that we need to trace Vswr circle in a clockwise direction. If you go further till in this way, and when you come across over here, here also you will get one more intersection point. Okay, I will denote it for time being. So if you travel the Vswr circle clockwise starting from ZL bar, you will get such a two intersection points in this particular case. Okay, so if I start traveling in this way, the another intersection of this VSWR circle I will get with unit resistance circle somewhere here. Okay, I will denote with black color over here. So that intersection point is this one, right? Okay, so if you visualize here, I plotted that particular point. So this point is also a valid design point. Okay, so you can choose either this point or this point in order to find the length of the stub. Okay, so this particular point will come as a first when we start from this, so it will result in minimum or smaller length of the location of the stub. So we will prefer to make use of a this particular point, although you can take this point also for the design. Okay, both are valid. Come back to the slide. Okay, now at this particular point again we need to read out the value of WTG. So what you do next step is read out the value of WTG at this intersection point number 1. So point number 1 we have got now. Now what you want is we want to find WTG value at point number 1. The same procedure is there. What you need to do is take the scale now. We'll take a ruler, connect the center of the Smith chart. I hope you people are following along with me. Connect the center of the Smith chart with point number 1, right? Connect the center of the Smith chart with point number 1 and extend the line on the periphery. Okay, what I am saying? Connect the center of the Smith chart with point number 1 and draw a straight line and extend it on the periphery of the external Smith chart. Okay, so I will choose the yellow color line again. Okay, and I will draw it in this way, right? And I will intersect at the periphery. Remove your scale. Now again, wherever I will zoom it out, wherever this yellow line is intersecting, we will read out WTG value. So the WTG value approximately we are going to get. So it is in between here. If you observe, it is between 0.32 to 0.33. right? So approximately 0.32, 322, 320. Okay, so 324, 326, 328, or approximately you can take lambda is equal to 0.326. So here this value could be near about 0.326. So I will take that value. So here I will write the WTG I got. So WTG is approximately 0.326 lambda approximately. So you might get somewhat a different value from this, but you should not get exactly altogether a different value. You should also get the same value near about 0.326. Some of you are might be getting a value 0.328. That is also correct. Okay, because it doesn't make much difference whatever value you'll get. But the only thing that you need to remember that you should not get too far value from this value, right? So here the first job is accomplished. So the first job is we have find out the location of the stub. So what is the location of the stub? The location of the stub is nothing but the difference of WTG values between these 2 points. Okay, so here I will denote. Okay, so here I will denote. So this gap. Okay, so I will denote with the arrow. So the distance from this line to this line. So this distance I am going to call it as a D. Okay. So what is small d? D is the separation distance between these two lines. So here in our slideshow, we will take the absolute difference between the values of wavelength towards generator at point number 1 and at point ZL bar. So if we take the subtraction, we know what is the WTG at ZL bar. We know what is the WTG at point number 1. We need to take absolute difference. Please remember. That means the subtraction will always result in a positive way. So 0.326 minus 0.306, we get the location of the stub is 0.02 lambda. Okay, so here I will write. So this D we have got 0. So here I will write 0.2 lambda. So the first job is over. So the first job is to locate the stub from the load. So please remember, from the load at a distance of 0.02 lambda, there is a location of our series stub. So the first half solution is over. The next job is to find out the length of the stub. Okay. So our next job is to find out the length of the stub. So let us follow the steps which are given in the PPT. Okay. So we need to find the imaginary value at point number 1. So at point number 1, already here in a blue color, we wrote down what is the imaginary value. We want to cancel this value. Okay. So that the value at point number 1 will become only 1. Okay. So what we need to do so that the value at point number 1 will become only 1 whenever we add the same reactance with opposite polarity. So if we add plus 1.39 into this point, so plus 1.39 will remove minus 1.39 and we are left with 1. This is what we want to make. So 1 is nothing but the center of the Smith chart. Okay, and this is how we can accomplish the impedance matching using a transmission line. Okay, so how to find the length of that particular transmission line? So here what we do is we will locate opposite value of the reactance. So the reactance here is a negative. We will take the same value of reactance but with opposite polarity. So what we do is we will plot a point which is representing pure reactance of value plus 1.39. So as per the slides over here, in order to cancel the reactance of minus 1.39, we locate the opposite reactance. Okay, so the opposite reactance will be exactly same in the magnitude but opposite in sign. So we will locate this reactance 1.39 positive, and we know that the positive reactance value will get relocated in the upper half of the Smith chart. Okay, we will plot this particular point which is only representing this reactance, and then at that particular point we will read out the wavelength toward generator, right? So we come back here in our Smith chart. Now the next step is we will locate reactance 1.39. Please remember only reactance, not the real part. Okay, so the reactance of 1.39 we can locate on the above half of the Smith chart. So here I will zoom out this Smith chart. Okay, so if you observe at this particular periphery, these are the reactance curves 1, 1.2, 1.4, and I want to locate a curve which is representing positive 1.39. So it will be closer somewhere to 1.4. Okay, so I will plot that particular point which is representing positive reactance value of 1.39 here. Okay, so and that point, let us denote that point with point number 2, right? So here it is a 1.4 over here. Okay, so 1.39 will be a little bit below that 1.4. So here I will take this, I will mark this position as a 1.39, right? So here I will write plus 1.39. So what this value is representing? This value is representing reactance. Please remember X value. Okay, so locate this particular point and read WTG value at this point. Okay, so how to read the WTG wavelength toward generator value at this particular point? This point, which is representing only reactance, need to be matched with the center of the Smith chart with a straight line. So what you do is, now again take your scale, right? Join the center of your Smith chart, join center of your Smith chart with this reactance point of 1.39 in this way, right? Approximately, and extend the line on the external periphery of the Smith chart, okay, with a straight line. So I will choose this yellow color again. All straight lines we are drawing with a yellow color in order to follow the same sign convention. Please remember. You can use some different color also if you want. So I'm drawing a straight line now, right, in this way. Okay, remove your scale and read the WTG value at the external intersection. So here I will zoom in now. Okay, so approximately what value of WTG we should get? Around 0.15 lambda. So here, see here, the straight line wherever it intersects to the outermost scale, it is exactly intersecting at 0.15 lambda. So here I will write the WTG at this reactance value is equal to 0.15 lambda. Okay, so you note down this value and near about the same WTG scale you are going to get. Okay, now next step is to find the length of the stub. So this is now important concept over here. Okay, so whatever we discussed, where to locate open circuit and short circuit point, so that concept now we will be utilizing. Now how to find the length of the stub? Okay, we already found out the location of the stub, which is given by small d over here. Okay, now the length of the stub. Now come back to the PowerPoint slide and let us see what it discussed. Now we locate the impedance short circuit point. So what we have plotted? We have plotted the impedance. Okay, so impedance we are playing with because we want to design a series stub. Okay, and what type of stub we want to design? The stub should be short circuit. Impedance short circuit point you need to find. Why impedance? Because we are designing series stub. As we are designing series stub, we will take into account impedance. Okay, and here we want to design a short circuit stub. Therefore we need to find where is the point representing impedance short circuit. Okay, so impedance short circuit means Z is equal to 0, right? So here try to locate in the Smith chart where is the point Z is equal to 0. Okay, as per earlier discussion, we know that this particular point on the extreme left hand side of your Smith chart, okay, in the innermost periphery of the Smith chart is representing Z is equal to 0, because here the impedance is minimum, and when you go along the real axis on the right hand side and when you reach at the extreme right hand side at this particular point, the Z will become infinity as an open circuit. So here what type of stub we are designing? We are designing series stub, so that's why we will consider Z or impedance, right? And the configuration of the stub is short circuit, therefore we need to consider impedance short circuit point. Now here we want to locate where is that particular point which is representing impedance short circuit. So the impedance short circuit point is represented over here. So I will denote that point with a black color again. I will increase the weight. Okay, so this is that particular point. Now recall why this is so from our earlier discussion in the PowerPoint. So what this point is representing? This point is representing Z is equal to 0. Z equal to 0. So why Z is equal to 0? Impedance, because we want to design series stub, so that's why impedance. And why it is equal to 0? Because we want to design a short circuit, so Z is equal to 0. So here also you can write this point as short circuit, SC. You can write in this way. Okay. Now read WTG at this particular point. Okay, now we already know that where is the location of our earlier marked WTG in order to find the length. So here we have placed that imaginary impedance. Okay, you need to just find where the location of this straight line from this line. Okay, so here you can clearly observe. I will draw it still in order to understand. So here we will start from this line, because this line is starting at Z is equal to 0, right? Okay, this particular, we will start with this point. Please remember, I will draw it. Okay, so the length of the stub is given by this particular gap. So how the length is given? From this particular impedance short circuit point to this particular straight line. So this particular distance, what I am showing with arc, and I will denote it with arrow later. Okay, so this is going to give us the length L of the stub. Okay, so what is the WTG over here at this starting point at Z is equal to 0? So we are starting from this particular line, so that means we need to consider WTG is equal to 0 lambda. So here WTG we need to take equal to 0 lambda, because we are starting from this line. From this line, this straight line is located at this distance. So here the reading is 0 lambda. What is the reading of WTG here? 0.5 lambda. If you take the difference between these two line WTG readings, you will get the length. So the same is done over here in the PowerPoint. So the difference in the WTGs at point Z is equal to 0 with point 2 here, absolutely 0 lambda minus 0.5 lambda, you need to take absolute difference. So 0.15 lambda. So if you take the difference of this WTG value with the WTG value over here, we will get the location of the length, right? So this will give us the length is equal to 0.15 lambda. Okay, so the solution that we have got is the location of the stub. We have got the location of the stub, that is denoted by small letter d, which we have calculated in our step number 7 and which is denoted in the Smith chart, right? So this will complete our design of the solution. Okay, and then afterwards whatever we have calculated, the length of the stub also we have calculated. The length of the stub is series short circuit configuration. and we have found out that the length of the stub is 0.15 lambda, and this is your complete design in your Smith chart, right? So what I will do is I will close this Smith chart now. Okay, then the last step is to design a circuit. Okay, to design a circuit, what we need to do is we need to come back to that configuration and repeat that configuration over here, and the circuit schematic for this particular example will look like this. Okay, so what we have over here, we have the load impedance 75 minus j 80 ohm, right? And this impedance is being matched with a 50 ohm impedance on the left hand side with a transmission line, right? Now for that purpose, we need to insert a series short circuit single stub in between load and transmission line, so that we have inserted. Okay, and how that stub is located? That stub is located at a specific distance from the load impedance, that is at d is equal to 0.02 lambda. Okay, and the length of that stub we have found 0.15 lambda, and this stub at the end it is short circuited. Okay, so this is a complete schematic diagram of what our single series short circuited stub look like. Okay, and this will complete the design procedure of single series short circuit stub. Okay, so what I request you people is the way in which we took the first design point, and as I already explained you that the same thing you can do with the second design point wherever it intersects the second point on the unit resistance circle. So I request you people to exercise the same design, but design by taking into account the second intersection point with the unit resistance circle and come out with another solution, right? So here you will get some different distance and some different length of the short circuit transmission line. So here I hope you understood the complete design procedure, how to design a single series short circuited stub. In our next lecture, okay, the similar type of example we will solve, but at that time we will take the parallel stub or design of shunt stub into account. Okay, so it is a little bit different procedure that we are going to see in our next lecture. So we will stop over here. Now again, welcome back to the 15th lecture, wherein we are going to see again some of the example of impedance matching circuit using a stub element. Okay, so in our previous example, we saw the design of single short circuit series stub, and we have concluded with this particular image. Okay, so in this tutorial, next tutorial or in next lecture, today we are going to see how to design a parallel stub, and that is with short circuit and open circuit configuration. Okay, so let us take one particular example in order to illustrate the concept. Okay, so I will continue over here in our next slide, and I will write the design statement for parallel stub. I'll duplicate the slide. Okay, and I will delete this slide, rather this slide also, because I want to start with a new slide. Okay, new slide. Okay, so I will put logo. Okay, so here design of shunt single, or we can write single shunt stub. Okay, we'll see open circuit as well as short circuit configuration for this design example in the same Smith chart, right? So let us write the problem statement over here. Okay, so for problem statement, what I will request you people is to I will take the example which is from my own book, and let us validate that particular example. If you recall last time while solving the single stub design example manually, we have not validated the design example using simulator tool, because please remember that in the simulator tool that we are using as a Vsmith simulator, there is a no provision to design a single stub. Huh? single series stub. Okay, but we can design single parallel stub over there. Okay, so let us take one particular example from my own book. Okay, so we'll open a particular example of single shunt stub. Okay, so we'll come to the page number, say around 200. These are examples that we started. Okay, so these are stub examples. So we'll be going through a couple of example. Okay, so let us take example of single short circuit stub in a particular example. Single parallel stub example I am looking out. So that the same example we will see, and let us see whether we get the same answer for this. Okay. So let me choose that example. What example we are going to take? Okay, so let us take this particular example and let us solve it manually, and let us see whether we get the same answer as that of the answers given in this book. Okay, and also we will validate our answer by solving it through using a simulator tool, right? Okay, so here I will write the problem statement now. Okay, so here I will write the problem statement. Design an impedance matching circuit using single shunt stub in open circuit and short circuit configuration to match ZL is equal to, now we'll take the example from the book. Now the ZL is given over here is 600 plus J300 ohm. Okay, so 600 plus J300 ohm with transmission line of characteristic impedance Z0. So the characteristic impedance of this transmission line is given and it is 300 ohms. Okay, so it is 300 ohms, right? Okay, so this is a typical problem statement. So the problem statement for design of single shunt stub is over here. So the problem statement says that we need to design an impedance matching circuit by using single short circuit, open circuit and short circuit configuration. Both configuration it is asked to match the given value of load impedance 600 plus J300 ohm with a transmission line whose characteristic impedance is 300 ohm. Okay, so first of all we will write the given data, right? What is the given thing? ZL is given, that is 600 plus J300 ohm, right? Z0 is given, characteristic impedance of a transmission line. Here it is 300 ohm. Please remember it is not 500 ohm. Okay. And the type of stub is single stub with shunt configuration, shunt, open circuit as well as short circuit they asked. Okay. Both solution. Okay. So let us go ahead and design this particular example using a new Smith chart, and here this is a design example of single stub shunt type of configuration. Okay, so here I will start a new slide for design procedure. Okay, and here I will continue. So here I will write the design procedure, right, step by step. So the design procedure or design steps. Okay, so the step number one. So the step number one is normalize and plot ZL. Okay, so after normalization, what we get? After normalization, we'll get small ZL is equal to the given value. What is the given value of complex load impedance? 600 plus J300, 600, right? Here I will write it is 600 plus J300 ohm divided by characteristic impedance 300 ohm. So what I will get, the value is 2 plus J1 or 2 plus simply J ohms. So we'll plot this point now. Okay, so for plotting this point again, please remember that you need to always start using a new brand Smith chart. So again, we'll be using Z chart. Okay, so what I will do is I will open a new Smith chart. I'll come over here and I will open a new Smith chart. Okay, so in this way. So a Z chart will be open for us. So a Z chart we will open. Okay, so this Z chart. Okay, so we will open this. So this is a new Smith chart I open, right? Okay, now plot this point as usual. The point is 2 plus J1 ohm. So quickly plot this point. You know how to plot. Real part is a 2 and imaginary part is a positive 1. So 2 plus J1 is this particular point. So I will take a pencil. I will increase the brightness so that we can visualize it clearly. 2 plus J1 is this particular point, right? So I will write this point as a normalized point, right? So this point is indicating ZL bar. Okay, so you also write along with me. So I have plotted the point 2 plus J1, which is representing ZL bar. Okay, so what is the next step? Now next step I will write in the slideshow. So the next step I will write over here. Okay, so read WTG value, or rather, first of all, check what type of stub is asked. Okay, so in the problem statement, what type of stub is asked? Shunt stub. Okay, if we are asked to design a shunt stub, we deal with admittance. Okay, we deal with admittance. So admittance is nothing but Y, which is a reciprocal of Z, please remember. So what we have plotted? We have plotted impedance. Okay, but we are asked to design a parallel stub or shunt stub. And from the general theory, general rules, we know that whenever we ask to design a parallel stub or shunt stub, then we need to deal with admittance. But what we plotted here, when we come back to the Smith chart over here, this is the impedance Smith chart, right? And we have plotted the impedance. But in order to design a shunt stub or a parallel stub, please remember, we need to make use of admittance rather than impedance. But we plotted the impedance. So this impedance we need to convert into admittance. So this is that additional procedure that we need to make in design option stub. Okay, so if on the other hand it could have been a series stub, we have been utilized this ZL impedance directly. But now in this second example, we are going to design a parallel stub. Okay, so this is the design example number 6. So here I will write so that we can understand. This is example 6, right? So this is a different. Okay, so what we plotted over here, we plotted the impedance and we want to design parallel stub. So that's why the next step is to transform or to convert this impedance into corresponding admittance. Okay, so how that can be done? So here I will write the procedure step. So we transform the plotted impedance to admittance using, so how to do that? Using VSWR circle. Okay, so see the procedure, how to convert the plotted impedance into corresponding admittance. So open your Smith chart. So what you do is take your scale, okay, join the center of the Smith chart with the plotted point, okay, in this way. Or you can skip using a scale also. You can directly take the compass. So instead of scale, what I will do is I will take the compass, put the center or the metallic part of the compass at the center of Smith chart. Okay, so what I'm doing, take your compass, put the metallic part of your compass at the center of the Smith chart exactly. Okay, in this way, take distance in your compass from the center of Smith chart to ZL bar. Okay, take distance in your compass from the center of Smith chart to ZL bar, right, in this way, and draw a constant VSWR circle. Okay, so there is no need to join the center of the Smith chart with ZL bar and again draw a VSWR circle. So directly you can take a compass, put the metallic part of the compass at the center of Smith chart and take the distance in your compass from the center to ZL bar and draw a constant VSWR circle. So I will draw this VSWR circle. I will choose the lime green color again as per the sign convention. Okay, so in this way you will get, right? So remove the compass now. So how to transform this impedance into admittance? The next procedure is take the scale. Now take the scale now, right? Join the ZL bar point with the center of Smith chart and extend the line on the other side of the VSWR circle and till it intersect the outer periphery of the Smith chart. So the next procedure is join the ZL bar point with the center of Smith chart, extend the straight line throughout. Okay, so I will adjust it properly first, right? Then I will choose the yellow color again as per the sign convention. Okay, I will use the yellow color. So I'm connecting ZL bar with the center of Smith chart and I'm extending that line straight away on the opposite side till it intersect external periphery of the Smith chart, right? So I will draw a line in this way. Say this procedure is impedance transformation. Okay, and then you remove your scale. So what I have done, I have joined the center of the Smith chart with ZL bar and I have drawn a straight line which straight away intersect the VSWR circle and the external periphery. Okay, so wherever this straight line, yellow line intersects the VSWR circle, okay, so this particular point we used to call it as a admittance point. So approximately this particular point we have got the admittance, right? So this admittance we will write this as a YL bar. So what we have done, we have converted the impedance into admittance. So please remember at this moment this Smith chart which was originally Z chart now got converted into admittance chart, or this chart we will call it as a Y chart. But please remember, for taking the sign convention of the imaginary part, we still follow the convention of impedance chart as per the original theory of design procedure. So here what we have done is we converted the impedance ZL bar to admittance. Why we have converted that? Because in the design of parallel stub, we need to deal with admittance. So the impedance we have converted into admittance. Okay, so here you need to read what is the value of WTG at YL bar, right? So here I will write the WTG value. Now you already know how to read the WTG value, right? So the WTG value over here you need to read between the outermost periphery. Now it is observed that it is between 0.46 and 0.47. So here it is 0.46 and it is around 0.462. So here I will write the WTG as whatever value we have got, WTG equal to 0.4, and I got one division ahead, 462 lambda. 462 lambda. Okay, so this is what the WTG we have got. So here I will write in our answer of theory. So WTG obtained, WTG stands for wavelength toward generator, obtained at YL, while bar, you can say, is how much? The value was 0.462, 0.462 lambda. Please remember. So I will insert a symbol for lambda. Okay, 0.462 lambda. So obtained value of WTG at while bar. Okay. So what is the next procedure? So here in the example also, again here in the actual example in the book, what value of lambda we have got? 0.464. Now here what we got? 0.462. So both are in a close agreement, right? So 0.462 we have got, there in the book we have got 0.464. So one and the same. So we have got near about the same answer and it is okay. Okay, so we move ahead. Then what is the next procedure? Next procedure is, take your pencil or pen, put your pencil or pen on while bar point, right? And start tracing out VSWR circle in a clockwise direction. So I will put my pencil on while bar and I will start tracing VSWR circle in a clockwise direction, please remember, till I intersect unit conductance circle. Okay, so where is the unit conductance circle? Unit conductance circle is this circle. Now why it became unit conductance circle? Because we have converted the impedance chart into admittance chart, right? So originally it is unit resistance circle. Now that unit resistance circle became unit conductance circle, please remember. So what I will do is I will denote with some other color the trace. So what I will do is I will go on tracing from YL bar. Okay. So I will go on tracing from YL bar in this way, clockwise. Please remember, always clockwise. See the arrow direction indicate that I am tracing from YL bar point the VSWR circle. Okay. So we need to trace up to what point? Till we get intersection with this unit conductance circle. So wherever it intersects, so here you can visualize clearly that this VSWR circle is intersecting over here. Okay, so I will plot that point there. Okay, so here I will plot this particular point. Let us call this point as a point number 1. Okay, so this is our design point. Okay, so what I did is from while bar I started moving on VSWR circle in a clockwise direction, which is shown with the red arrow. Okay, till I get intersection with unit conductance circle. Please remember, this is now is called as a unit conductance circle because we have transformed the impedance chart into admittance chart. So hence the unit resistance circle became unit conductance circle, right? So when we find the intersection with unit conductance circle, that point we denote with 1. Okay, so you need to write the admittance at point number 1. So here I will write here, we trace VSWR circle clockwise from while bar till we get intersection with unit conductance circle. At this point we write y1 bar. So this y1 bar real part will be always 1. Okay, so please remember while taking the imaginary part, so here what is the real part at point number 1, which is indicating y1. Okay, so at point 1 we need to write admittance. Now the admittance real part will be 1. Okay, and what is the admittance imaginary part? We need to follow the sign convention of original Z chart, please remember. So the imaginary part is again 1, and this imaginary part is 1 because we are following the sign convention of impedance chart, though it is admittance, right? So here I will get the value of admittance at point number 1, it is 1 plus 1j. So I will write over here. So I will get the real part as a 1 and imaginary part is plus remember, okay, plus J1 because I am following the sign convention of still impedance chart. So in the upper half of the impedance, the imaginary values are treated as a positive. So the same, okay. So I got 1 plus J1, okay. So this is a admittance, okay. So with WTG, so you need to read WTG at point number 1. Okay, so come back again to your Smith chart. We have plotted, we have wrote down what is the real value and what is the imaginary value at point number 1 in terms of admittance. Now the next procedure is to find out what is the value of wavelength towards generator at this point number 1. Okay, so for that again you need to take your scale. So the scale is over here. Okay, now what you do is join the center of the Smith chart with this particular point. Join the center of Smith chart with this particular point number 1 in this way. I will zoom in a little bit. So point number 1 and center of the Smith chart need to be exactly connected. Okay, so and then what you need to do is you join the center of the Smith chart with point number 1 and draw a straight line extending on the outer periphery of the Smith chart. So I will again choose this yellow color. I will join the center of Smith chart now with point number 1 with a straight line, and I will extend the line on the external periphery of the Smith chart in this way. If you are observing, I am drawing a straight line. Okay. After that, you remove the scale. Okay. So here, wherever the center of the Smith chart, the connected straight line from the center of Smith chart to point number 1. Okay. So in this way, center of the Smith chart to point number 1, we have connected with a straight line with a yellow color line. Okay. So wherever it intersects at the outer periphery, there you need to read WTG value. So here the WTG value, I will read the WTG value here. I will write here how much it is equal to. Now, if you clearly observe, it is one division above 0.16. Okay, it is 0.162 directly. 0.162 lambda. 0.162 lambda approximately. Okay, so that value I will write in my solution. The WTG I got 0.162 lambda. So I will insert a symbol again. Okay, so 0.162 lambda. Okay, so what you need to do is you need to find the location of the stub. So in the fifth step, hence the location or position of shunt stub. How it is given? It is given by the absolute difference between the WTG reading at while bar and WTG reading at point 1. So open your Smith chart. Okay, now here, if you visualize it clearly, okay, I will zoom in a little bit. Okay, so here you can clearly observe the WTG reading at while bar and the WTG reading at point number 1. If you take the difference between these two lines, you will get the location of the stub. Okay, so here first of all, I will denote the location by drawing an arc. Okay, so what I will do is, see, this distance between two lines, which I have shown with arrow diagram, is going to give us the distance t. Okay, so but how to take? We are not going to take the simple subtraction, because please remember, in between this straight line and this straight line there is a zero scale. Okay, so I will denote it also over here. Okay, so where is a 0 lambda line? It is exactly on the horizontal line over here. in this way. Okay, so I will choose a color again, yellow color. Okay, so this is a horizontal line. Okay, so what is the WTG at this horizontal line? It is 0 lambda. So this point is just below this 0 lambda. So that means from this point we are approaching to this line. Okay, so this total distance d can be divided into two paths. Okay, so what is that? So I will denote here. It can be given as distance between these two straight lines, right? In this way, plus the distance between these two straight lines. Okay, so please remember you need to take the separation between this straight line and this straight line as the two subsection. So this complete separation between these two straight line is divided into two parts, from this straight line to this horizontal real axis, and from this horizontal real axis to this straight line. Okay, so what we do is here, what is the reading when you are approaching to this straight line? The WTG value over here is 0.5 lambda, right? So how this distance is given? Which one? The distance between these two lines. The distance between these two lines is 0.5 minus 0.462, so that here you will get this distance. So here I will write the equation. So first 0.5 minus 0.462 lambda, bracket complete, lambda. Okay, so this is the first path, right? And in this distance we need to add the next distance. So what is the next distance? From 0.5 to this particular line. Okay, so when you start from this particular horizontal line, we need to take WTG as 0 lambda now. Okay, because we are starting from this point. So starting from this point, when we start this as a 0 lambda, this line is located directly at 0.162. Okay, so directly you can add. So here I hope that you understood how to take the separation distance between these two lines when they are separated with a 0 lambda line. Okay, 0.162 lambda, because 0.162 minus 0 lambda will give the same. I will insert the lambda symbol. Okay, so how much this will come? So here 0.5, the first half distance, minus 0.462, right? And this is added with 0.162 lambda. So it will give me 0.2 lambda. Okay, once again I will do. First we need to take the difference between 0.5 minus 0.462. Okay, and this is to be added with 0.162. It will give you 0.2 lambda. Okay, so my location of the stub is 0.2 lambda, please remember. Okay, so we have calculated the first half of the solution. So the location of the stub, that we denote with the letter D. Now here you can visualize in our Smith chart. So this complete location is given by D. So the separation between this straight line passing through while bar and the straight line passing through design point number 1. So that is the total distance D. Okay, so here the next job is to find out the length of the stub. So how to find the length of the stub? Again, in order to find out the length of the stub, you need to remove the imaginary part at point number 1. Coming back to our slideshow. Okay, so next job, sixth job, is to find the length of the stub. Okay, in order to find the length of the stub, we know that the imaginary part at point number 1 is plus j1. We want to make this y1 purely equal to 1. So what we should do, so that y1 value will become 1. So in the Smith chart, y1 is nothing but y1 bar, right? So in order to make this value completely equal to 1, when we add minus j1 over here, minus j reactance, or here we are dealing with admittance, that means minus J1 is indicating susceptance, please remember. So when we add, so here I write that when we add susceptance, right, susceptance of value opposite but same magnitude. So opposite means minus, and what is the same magnitude? J1. Okay, so please remember here, what is the magnitude of susceptance? Plus J1. Okay, if we want to cancel it out, I need to add minus J1 so that the real part 1 only remains. So that is what our target. So when we add a susceptance value of minus J1, we will find length of the stub. So next procedure is plot minus J1 susceptance and denote it with 0.2. Okay, so what we do is we will plot negative susceptance of value 1 and denote that point as point number 2. So again, come back to your Smith chart. So here we need to locate minus J1, please remember. So again, we need to follow the sign convention of original Smith chart. So minus J1 is a imaginary part. So as per the sign convention of Z chart, it will come somewhere in the downside or the lower half of the Smith chart. So minus J1 point. So here where you will locate the minus J1 point over here. Okay. So if you zoom in over here, the negative susceptance is indicated over here. Okay, so please remember again, we are following the sign convention of impedance chart originally, but still we are calling it as a admittance, right? So here I will denote that point. Okay, so this point is over here. Okay, so what is the value? You need to also write this value. The value is minus J1, and what this indicates? This indicates point number 2. Okay, so the value of this point number 2 is only a susceptance. It has only a imaginary value, no real value. So that's why it comes on the periphery. Okay, so when we plot that, we read WTG at that point. Okay, and here we write and we read WTG at point 2. Okay, so what WTG we get there? Let us write WTG is equal to whatever value we will get over there. Okay, so in order to read WTG value at point number 2, what we need to do next is take your scale. Okay, so take your scale plus ruler. Okay, I'll bring it down. Okay, and now you connect the center of Smith chart with this imaginary susceptance value. In this way, right? So what you do is you connect the center of Smith chart with this negative susceptance value and extend the line on outer periphery of the Smith chart. So I will again choose this yellow color line, the same sign convention, and draw a straight line from the center of Smith chart to that susceptance negative point and extend the straight line. Remove the scale. Okay. Now here what you do is you read WTG value wherever it intersect on the outer periphery. So here it is in between 0.37 to 0.38. Okay. So here I will write what is the WTG value. So WTG value here I will write over here at point number 2, the WTG is equal to, say it is clearly between 0.37 and 0.38. 0.37, 1, 2, 2 and half, 0.372, 374, 0.375 approximately, 0.375 lambda. Please remember. So I will write this value in my solution. So WTG I have got 0.375 lambda. I will insert the symbol again. So I got 0.375 lambda. So how to calculate the length of the stub then? In the seventh step, hence the length of admittance, please remember, admittance short circuit stub. Why admittance? Because it is a parallel stub, okay? And it is given us design two solutions, short circuit and open circuit. Let us first say open circuit stub length, okay? So here, rather than admittance, what I will write is length of shunt short circuit stub. So for shunt, we need to deal with admittance, right? That is Y. And short circuit means Y is equal to 0 point. Okay, so first of all, you locate Y is equal to 0 point on the Smith chart. Okay, this is your Smith chart. Okay, so where is Y is equal to 0? So here we know that, so here I will remove the scale. So Y is equal to 0. Where is Y is equal to 0 point? So it is located on the real axis of our Smith chart. So here we know that here the impedance is 0. That means Y is equal to infinity. And here at this particular point, the impedance is infinity. That means Y is equal to 0. Okay, so here I will place the ruler now. So I will take this ruler, and Y is equal to 0 point is located on the right hand side extreme on the real axis. Okay, so where is over here. Okay, so here I will choose some different, I will say, let us choose, I will take a purple color, this line. Okay, so what is the WTG at this point? The WTG at this particular point, now here I will write, what is this point is representing? This point is representing Y is equal to 0. Or in short, it is representing admittance short circuit point. Okay, because this point will help us to calculate the length of short circuit stub. Okay, so here it is 0.25 lambda. Here I will also write it 0.25 lambda. Okay, so at admittance short circuit, this is 0.25 lambda. So you need to find out the location separation of this imaginary point WTG with this admittance short circuit point. So here you will get the first solution. Okay, I will choose this color. So the separation between these two lines, this one and this one, from admittance short circuit point. So this will give us the first solution, and this is a length for short circuit SC. I will write. Okay, so if you take the difference between the WTG values of this imaginary point and WTG point of Y is equal to 0 point, you will get length of short circuit stub. So here I will write, so length of short circuit stub, so I will write L, in bracket I will write short circuit because it is a short circuit length. So how it is given? It is simply given the difference between this WTG and this WTG. So 0.375 minus 0.25. So here I will come back 0.375 minus 0.25 lambda. Okay, so 0.375, you take the absolute subtraction, 0.375 minus 0.25 lambda. So how much it gives? 0.125 lambda. So here I will write 0.125 lambda. I will insert a symbol and I will close. Okay, so this is one solution of finding the short circuit length of parallel stub. Okay, so there is another mechanism. Okay, so we are asked to find the open circuit length also. Hence I will write the length of shunt. Now open circuit, how to find it? Open circuit stub. Now open circuit, what type of stub we are dealing with? Admittance, sorry, shunt or parallel. So for shunt or parallel stub, we deal with admittance. Okay, open circuit means it should be infinity, right? Okay, so what it represent? It represent that it is open circuit. So we need to calculate the length L. In that particular case, it is an open circuit condition. Okay. So you need to find open circuit position for the admittance in the given Smith chart. So open the Smith chart. Where is y is equal to infinity point? Y is equal to 0 point is over here. So definitely y is equal to infinity point is located over here. So the same point on the left hand side. So here I will denote. So this point is nothing but y is equal to infinity. Okay. Now from this infinity straight line, the length of this particular, so whole way, so I need to travel in this way from y is equal to infinity to this particular straight line where the impedance is located. So this particular, the whole traveling of the circle nearly from this straight line representing y is equal to infinity to that impedance point will give us the length of open circuit stub. OC I will write. Okay. So definitely when we start with this particular axis, the reading is 0 lambda, and directly this reading will give us 0.375 lambda minus 0 lambda, that is the same 0.375 lambda. So here I will write 0.375 lambda. Okay. So here we have completed the solution. We have designed the entire single parallel shunt stub with both configuration. We saw how to design open circuit configuration and short circuit configuration in the same Smith chart. Okay. So I hope you understood how to design. So when we insert that particular stub of appropriate length, what will happen is this particular path will get traveled in this way, and ultimately it will come at the center of the Smith chart and it will get decided at the center of the Smith chart, and we will get a matching. So the red arrows are indicating how the matching is accomplished, right? So from while bar it will go to design point, and from the design point when we insert appropriate length of the stub, this point will get transformed at the center of the Smith chart, and thus the matching is achieved. Okay. So this completes the example of design of parallel stub or shunt stub in both configuration, open circuit and short circuit. I will save this and I will close this app. Okay. Now the last part that is remaining is to draw the diagram. Okay. So last part is to draw the diagram. So I will draw the diagram on the new slide. Okay. So for drawing a diagram, I will take the reference of the same diagram over here. Okay. So I will select those two configuration. So rather I will select both of this because we need both of these diagrams. Okay. I will copy this diagram. Okay. And I will bring those diagrams over here. Right. I will take a little bit over here. And here I will mention this as a circuit schematic. Circuit schematic for example. So this is example number 6, right? This is example number 6. Because in example 6, we saw the design of parallel single stub with open circuit and short circuit configuration. Okay. So here you need to write the values, what you have got, right? So the values that we have got is the distance that is going to remain same. Okay. So the distance in both cases is 0.2 lambda. Okay. So here I will write, so the distance in both cases. So what I will do is here I will write what distance we have got for the first case, that is the same 0 point, how much it was, 0 0.2 lambda, right? So this distance, right, 0.2 lambda, right? And it is common for both. What I will do is I will increase this one a little bit further. 0 small d is equal to 0.2, and I will insert the symbol lambda. Okay, 0.2 lambda, and here it is also same, because the distance is not going to change. The distance will remain same. The location of the stub is common for both configuration. D is equal to 0.2 lambda. I will insert a symbol again, right? Now, what open circuit length we have calculated? Come back to the solution. Here, we have calculated the open circuit length of the stub. First the short circuit length of the stub, 0.125 lambda. Okay, so here the short circuit. So this length is, so what I will do is, here I will write, so this length 0.125 lambda, 0.125. Okay, and I will insert the symbol also for the length. Okay, insert, close. Okay, so this is the length of short circuit configuration. And similarly, what length of open circuit configuration we have got? 0.375 lambda. Okay, so again to show the same over here, the open circuit configuration. So in the open circuit configuration, I have got the length equal to 0.375 lambda. 0.375 lambda. I will insert a symbol again. Okay, and this will give us the complete solution of the example number 6, in which we have designed a single, parallel or shunt stub for matching the given value of load impedance with characteristic impedance of transmission line. So here the characteristic impedance of the transmission line Z0 was 300 ohm, right? Right here Z0 was 300 ohm and the ZL was 600 plus J 300 ohm. Okay, so J 300 ohm. Okay, so this was the example. So we have matched, or we have designed the impedance matching network using parallel stub to match the complex load impedance 600 plus J 300 ohm with 300 ohm transmission line using a parallel or shunt single stub in both configuration, open circuit as well as short circuit. Okay, so what values we have got over here? See the values that we have got over here. Now in this particular solved example, so this is designed with a short circuit. Okay, so see here, if you observe, the required length of the stub over here is 0.125 lambda, short circuit length. Okay, so what length we have got for our short circuit case? It is same, 0.125 lambda. Okay, and what is the distance or location of the stub he has got in the solution which is given in the book? So the location of the stub, they have got 0.198 lambda. Okay, so in our case we have got the location of stub 0.2 lambda, which is again close to 0.198. Okay, so this agrees the solution that we have calculated manually. Okay, so in short, within a 5 minute I will show you how to simulate the same using a simulator and how to verify our answer. Okay, so again, so within a no moment and within a 5 minutes, I will illustrate you how to simulate this, and we will validate our solution with the simulated result. So I will close this now, because manually, whatever values we have calculated manually, those are exactly matching with our solution given in the book.